In my previous video, I talked about polymers and how do they differ from each other. In this video, I am going to talk about typical properties of polymers. The properties I am going to discuss today are thermal, mechanical, rheological, optical, and electrical properties. A good understanding of these properties helps to select the right polymer for the right application and also the right condition to make those products. So let's start with the thermal properties. Thermal properties are very important because thermal behavior of polymer provide temperature limit in which it can be safely used. It also helps to determine their processing condition. Polymer typically shows three transition points. First one is glass transition temperature, which is also known as TG. This is a temperature at which the polymer transitions from a brittle glass-like material to rubbery material, which can be stretched or bent. Why it is so? Because below Tg, polymer have only vibrational motion. As a result, when we try to bend or deform them, we have to break all the chains. Above Tg, polymeric material gains segmental mobility, which means a small segment of the chain can bend or rotate. So polymer can be bent or deformed above Tg. Second important transition is crystallization temperature, which is also known as Tc. At Tc, the random polymer chains in amorphous state form highly ordered crystalline phase. Tc is a very important factor during product manufacturing process, as it helps to decide mold temperature and cooling time. Third important transition temperature is melting temperature or Tm. At Tm, crystals melt and form randomly oriented free flowing polymer melt. Tm of a polymer helps to decide the processing temperature. Typically, Tm plus 50 degrees C is used as processing temperature. The thermal transition temperatures Tg, Tm and Tc depends on chain flexibility, which is related to monomer type and percentage crystallinity. To know more about glass transition and crystallization, please watch our videos on these topics. Now coming to the mechanical property, which is the most important property of polymer for its different applications. Mechanical properties of polymer is typically represented by three parameters: tensile strength, modulus, and toughness. The strength of a material is the stress value at which it breaks, whereas modulus is the ratio between stress and strain, and typically represent material's ability to resist deformation. And toughness is the amount of energy consumed by the material before it breaks. It is mainly measured by the area under the stress-strain curve. Polymers can be broadly classified into three categories: brittle, plastic, and elastomers. From the graph, it is very clear that brittle polymers show very high strength but very little flexibility. Highly cross-linked polymers usually show this kind of behavior, whereas elastomers are like rubber. It shows very high deformation at significantly lower stress. Plastics are regular polymer which we use in our daily life. They show very unique deformation behavior. During initial stage, very high stress is required to deform them, but after reaching yield point, it shows less resistance to deformation. And after reaching certain level of deformation, it shows more resistance to deformation. And finally, breaks at higher stress value than yield point. Next is the rheological property. Rheological property of polymer significantly differ from metal and common fluids. Flow behavior of polymer, both in solid and melt state, depends on percentage strain, which means how much material have been stretched, and on time, which means how long load have been applied. Most polymer melts are non-Newtonian fluid because they do not show linear correlation between stress and strain. The reason for this is viscosity of polymeric material changes with changing strain level. In the right graph, we can see that viscosity of polymer changes from Newtonian behavior to very low viscosity at high strain rate. The change in viscosity is the result of chain disentanglement and orientation in the stress direction. Majority of the polymers show either shear thinning behavior, which means decrease in viscosity at higher strain rate, or shear thickening behavior, which means increase in viscosity at higher strain rate. Depending upon application, like during polymer processing, shear thinning behavior is preferred as it reduces the amount of energy required to process the material. But in case of paints, shear thickening behavior is preferred so that paints do not drop or flow from the wall. Optical properties of polymer is very important for consumer goods like glasses, water bottle, packaging film, etc. Optical properties of polymer can be controlled by product manufacturing processes because during the process we can select a condition to have a fully amorphous or a semi-crystalline polymer. As amorphous polymers are homogeneous materials, they allow light to pass through without significant loss in intensity. Whereas in semi-crystalline polymer, majority of light is scattered by the crystals, so they appear opaque. Depending upon the end application, we can modify the optical properties of polymer. Polymeric materials significantly differ from metals in their electric properties. Unlike metals, majority of polymers are insulators, that is, they do not allow transfer of electrons. Due to their insulating nature, polymers have wide range of applications. However, for certain applications like electronics, wire and cable, EMI shielding, polymeric materials need to have certain amount of conductivity, typically in the range of 10 to the power minus 9 to 10 to the power minus 2 Siemens per centimeter. This range of conductivity can be achieved by mixing conducting fillers in the polymer matrix. There are also a class of polymer known as electroactive or conducting polymers, which possess inherent conductivity. However, because of their high cost and processing issues, they have only limited application.